No matter what kind of function you're working with, it's often important to know what are the minimum and maximum values that that function produces. So for example, if you have a function that represents the height of a weather balloon as a function of time, you might want to know how high that weather balloon gets, and that would be the highest point, and that is the maximum output of this function h of t. If you have a function t of x that represents the temperature of a metal rod, x units from one end, you might want to know where is the metal rod coldest, and that would be the minimum value, or the minimum output value of this function for all x values. If you have a function p of x that tells you the profit you earn if you produce and sell x units of your product, you might want to find the maximum, or find the production level x that gives you the maximum profit, because you want to maximize your profit. So that you would want to find a maximum value for the function p of x. So you can see in all of these examples, what ties them together is that we're interested in finding the minimum value and the maximum value of a function. It turns out if you can find a maximum, you can find a minimum. So we'll think about the two of these simultaneously, even though often you only care about a minimum or a maximum and not both. Well, it turns out that there are really two kinds of minimums and maximums. There's an absolute maximum. An absolute maximum is just the largest, the highest output value anywhere on a function. So if we look at this graph here, let's assume that the graph sort of continues up at the ends there. Let's think about an absolute maximum. So we have to ask ourselves, on this graph, is there a single point that is higher than anywhere else on the graph? Well, definitely down here, these points aren't higher than anything else because there are higher points nearby. But what about this spot at the top of the hill here? Well, that is a high spot, but it's not the highest point anywhere, because way over here on the right and way over here on the left, there are higher spots. They aren't nearby, but they are higher. Are these absolute maximums? Well, no, these aren't absolute maximums either, because if you go a little bit further out, you can get even higher up on the graph. So this particular graph actually doesn't have an absolute maximum. There's no single point, or there's no height that is the highest height on the graph. All right, well, what about an absolute minimum? An absolute minimum is the smallest output anywhere on the graph. Well, you can see there's sort of two possibilities. There's this low point over here and this low point over here. But one of these is lower than the other, right? This one here, it looks like it's maybe minus, it's hard to say, minus a quarter or something like that, minus 0.2. That's the lowest output anywhere on this graph. This graph, nowhere on this graph is lower than this spot right here. So the absolute minimum on this graph, it looks like it's about x is, I want to say maybe that's 0.4 if I'm reading the scale on this graph correctly. So approximately 0.4. So this is the location of the absolute minimum. And the actual output value of the absolute minimum looks like it's maybe minus 3. So there's a minimum of minus 3 at the x value, 0.4. So those are absolute minimums and maximums. But there's another flavor of minimums and maximums called local minimums and maximums. So a local maximum, for example, is the largest output not everywhere, but just nearby. And what I mean by nearby is on some interval around the maximum. So a local maximum is a maximum if you only look near the point that you think is the maximum. Well, this is a high spot here. Is this a local maximum? So we can put an interval around it, and if we only look on the part of the graph in this interval, then this point is the highest thing on this part of the graph. And so that means that this is a local maximum. So it looks like there's a local maximum at x equals, I don't know, 4.2 maybe. All right, and a local minimum is the same thing, but for the smallest output nearby instead of the largest output nearby. And on this graph, there are two local minimums, right? There's the one over here that's an absolute minimum. If we restrict the graph only to the part of the graph near this low spot, it is the lowest thing on that part. And so there's a local minimum at x equals minus 0.4. Oh, this should be a minus 0.4 up here. But there's another one. There's another local minimum at about 8.4. That's this one over here. Because if we put an interval around it and look at the graph only on that interval, then our local minimum is the lowest thing on that part of the graph. So in any given application, whether you want the absolute minimum and maximum or the local minimum and maximum, really depends on what you're doing. So you kind of just have to pay attention to the context. But what we'll do for now is try to decide in general how can we find absolute minimums and maximums. Well, before we go looking for absolute minimums and maximums, maybe we should try to guarantee that a function actually has absolute minimums and maximums. This graph shows you that it's actually very possible for a function to not have an absolute maximum. It's also possible for a function to not have an absolute minimum. Think of, say, the function y equals x cubed. The graph of that looks like this. This function doesn't have an absolute maximum or an absolute minimum. So maybe what we should do is try to sort of add some conditions or some hypotheses about our functions that will force them to have an absolute maximum and absolute minimum. Well, there's a handy theorem about continuous functions that tells us that a function will have an absolute minimum and maximum. And this theorem is actually kind of difficult to prove, so I'm not going to prove it, but you'll have to take my word for it. It's called the extreme value theorem. And the extreme value theorem says that if you have a continuous function on a closed and bounded interval, then it has an absolute minimum and maximum somewhere on the interval. So by closed, what I mean is just that this interval has to include, it includes its endpoints. And by bounded, I mean it's finite. It doesn't fly off to infinity to the right or to the left. So, for example, this interval right here is closed because I've included the endpoints, and it's bounded because it doesn't fly off to the right or off to the left forever. So you can get a feel for why the extreme value theorem has to be true if you just play with some examples. So on this closed bounded interval, let's draw a continuous graph. So let's try to draw a graph over this interval. No matter how you draw your graph, maybe like this, or like this, or even, I don't know, something like this. No matter how you draw a graph on this closed and bounded interval, as long as it's continuous, it will have an absolute maximum. So for this one, the absolute maximum is there, it looks like. For this one, the absolute maximum is there, all the way over at one of the endpoints. And let's see, for my third one, it looks like the absolute maximum is maybe right here. These three graphs also have absolute minimums. For the first one, it looks like it's there. For the second one, it looks like the absolute minimum is all the way at the other endpoint. And for the third one, it's hard to tell. Maybe the absolute minimum is right there, but it might also be over here. It's a little hard to tell. But one of these two spots will be the absolute minimum. So you can kind of see that having a closed and bounded interval just kind of makes you draw enough of a graph that it will have an absolute minimum and maximum. But let's look at some other examples to see why these assumptions, continuity, closed interval, and bounded interval, really are necessary, or they really are necessary to force the existence of absolute minimums and maximums. So first, let's try an interval that isn't closed. So what we're going to do is, this interval is bounded. What we're going to do is draw a continuous function on this non-closed interval that does not have absolute minimums or maximums. Well, from previous experience with other graphs, we can have there not be an absolute minimum or maximum if the graph just flies up forever to infinity. Well, we can make that happen if we say start in the middle and then just go like this. This wasn't possible when the interval was closed because, right, we have this vertical asymptote, and this function isn't defined at the x value that produces this asymptote. That would be a problem if the interval were closed, because we have to define the function at the endpoint, since the endpoint is part of the domain. But if the interval isn't closed, we don't have to define the function at the endpoint, and that's what lets us get away with having this vertical asymptote. And we can do the same thing going the other way, but with a vertical asymptote going down. So here's a continuous function on a bounded interval, but the interval isn't closed, and this function has no absolute minimum or maximum. So you can see we really do need this closed condition for the extreme value theorem. All right, so that's closed. What about an interval that's not bounded? I probably should draw it so that it's not bounded. Well, if it's not bounded, we have lots of room to make the function just keep going up. So we could just do a straight line like this. Right? Since the interval is not bounded, it just goes up and up and up to the right, and so there's no absolute maximum. And so, similarly, off to the left, it goes down and down and down, and so there's no absolute minimum. So having a bounded interval really is necessary for the extreme value theorem. Finally, let's look at continuity. Well, if your function isn't continuous, you're free to jump around, and that gives you a lot of options for how you can prevent there from being absolute minimums and maximums. Here's just one example. So this function is definitely not continuous because of the jump discontinuities, but it doesn't have any, it doesn't have an absolute maximum, right? Because you might think, well, look, all we have to do is get really close to that top spot, but this spot isn't the highest spot. There's one a little higher. But this isn't the highest either. You can get a little higher there, and a little higher, and a little higher. Because this open circle is missing from the graph, it's actually possible to get closer and closer and closer to it, but we can never land on that spot because the function doesn't have this point on the graph, right? The function jumps down to this point. So this doesn't have an absolute maximum. No matter what point you suggest as the maximum, there's a point that's a little bit higher. And then the same thing happens for an absolute minimum as you sort of approach this lower spot down here. No matter what point you might think is the absolute minimum, you can get a little bit lower just by creeping a tiny bit closer to this open circle here. So we do need our functions to be continuous for the extreme value theorem to be true. All right, so remember we were thinking about finding absolute minimums and maximums. So before we actually do any calculation, we'll just really quickly check with the extreme value theorem to make sure that there actually are absolute minimums and maximums for us to find. One good thing about the extreme value theorem is that it's very easy to check. Right? Most functions that we write down are continuous wherever they're defined, and when they aren't defined, we usually will notice. And closed and bounded intervals are pretty easy to come by. Those are just intervals that look like an interval from a to b that includes the endpoints, and a and b have to be finite numbers. Neither of them can be infinite. So the extreme value theorem is actually a pretty easy theorem to satisfy. And so for many, many examples, we will have absolute minimums and absolute maximums.